to have Hari Krishnan Ramani from Stanford is going to, and he agreed to come here on very short notice, and we appreciate that. And we're looking forward to a seminar on dark matter detection with trapped ions.
Yeah, thank you for having me. I'm Hari. I'm at Stanford University, and this talk is titled Dark Matter Detection with Trapped Ions, and yeah, this is obviously work done by me. I'm very proud to say that there's also work done with experimentalists, so I'm going to show you some real data from these experiments, and show you some limits we have been able to set. And also want to highlight some grad students, both on the experimental and theory side, who worked hard on these projects. It's a very ambitious plan that I have, but I don't have to get to the second part of the talk. Please feel free to ask questions. Let's make it interactive. The rough plan is I'll be talking about this dark matter model called Photon Dark Matter, and then I'll introduce these electron traps, which seem to be ideal places to be looking for these things. I'll show some preliminary results from our pilot experiment, from our collaboration, as well as make projections for the future. And then in the second part of the talk, if time permits, I'll be talking about Millicharged relics. And then I'll talk about a close cousin of the electron trap called the ion trap, which many, if there are any MO people here, might be more familiar with, and show you results and projections as well. This, I'm sure many of you, you've heard many talks over, but a lightning introduction to what we're thinking about. There's a lot of dark matter out there. We don't know what it is. Right? We know its density. We think we know its density at least, which is roughly 0.3 Joule per centimeter cube. Right? We don't know what its mass is. We have no clue. There are some theoretical motivations. So a lot of the dark matter detection and other schemes went after the hundreds of GeV to the TeV range because of what's called the WIMP miracle. Right? Going to even higher masses, there is a unitarity limit roughly around 100 TeV or so. Right? I will not be going in that direction, instead in the lower direction. So you might have heard some talks about, say, sub-GeV dark matter, which are in vogue now. People think about capital MEV or KEV dark matter. Experiments like Sensei, Super CDMS, things like that work in this mass range, right? Below KEV, something interesting happens, which is that you can only have bosons as dark matter. And that can also not go all the way. Roughly around 10 to the minus 21, 10 to the minus 22 EV or so, you have dwarf galaxies, and the fact that we see dark matter in dwarf galaxies means that you must be able to pack dark matter inside these compact objects. That sets a 10 to the minus 21 EV limit. So this is our playground in some sense. Today's talk will be roughly at the milli EV range, and I'll tell you why I'm thinking about the milli EV, why it's tricky, etc. Okay. So specifically, you saw that in this previous slide, as soon as we talk about bosons, the theory should make sense in that the mass is really light, right? Why is this mass really light? Could be a natural question. And axions and dark photons have symmetries that protect this light mass. So it's good to consider such bosons in this low mass range.
Can I ask a simple question?
Yeah, please.
I see for the galactic center densities, some literature will use 0.3, some will use 0.4.
Yeah.
How well do we know the density?
If you don't, local, it could be like, 0, right? You could think of some crazy theory, like in the solar system, we have no clue what it is.
Oh, I have no clue. Okay,
right,
okay.
Right? So it's only like roughly, I think a kiloparsec circle around us is roughly a GeV per centimeter cube. Right, and then you write the NFW profile, and you are making a projection to. So if someone tells you they know 0.3 or 0.4, they're lying to you. Also think about the order of magnitude problems you're dealing with, right?
Okay.
It's such that this doesn't become that important a problem to think about whether it's 0.3 or 0.4. Right?
Okay, got it.
It always is degenerate with some other parameter in your problem. If you discover dark matter, we have the good fortune, then we would actually be able to answer this question.
Okay.
Pretty well. Thank you. Yeah. So let me talk about photon dark matter. So it's a very simple model to write down, right? So as soon as you hear the words dark photon, so it's very similar to a photon. So let me write a U1 theory down. So it has the F prime kinetic term, right? But it is dark matter, right? Not dark radiation, which means I have to put a mass down. Let me put that mass down. It has ma prime square, a prime. So that's what that's a main differentiator from a regular photon that we are used to. This guy has a dark has a mass. Right? It has a mass, and it's going to be non-relativistic. Okay? But what is interesting is that you can ask, okay, does dark matter exist? Oftentimes, the next question is, how does it talk to the standard model? Right? That's the next question we need to ask in order to see if we can detect this dark matter. Okay? So, one thing you can write down is this kinetic mixing parameter. Is there a You can write this kinetic mixing parameter down, epsilon f prime. Here, all the primes are dark matter terms, and no prime is the standard model. Okay. So I've written this kinetic mixing parameter down, f prime, right? And it's allowed by gauge invariance, by the individual U1s. This particular term is allowed. Furthermore, if you have a UV theory that helps you make this connection, let's say some charge is bifundamental under both the standard model U1 and the dark U1, you're only logarithmically sensitive to the UV of the theory. This kinetic term you write down. Furthermore, what is one important thing for dark matter? It has to be stable. If Ma prime, the mass of the dark photon, is much smaller than twice the electron mass, it can only decay to 3 photons in this theory. A single dark photon decaying to 3 photons. There are no other standard model particles it can decay into. Right? And as a result, its decay is so slow that it becomes metastable and stable over the age of the universe. There are several production mechanisms people have thought about. I mean, and you can look through this. Clearly, it's a very active topic that people are thinking about. Like, what is the formation mechanisms? What happens to them subsequently? People have thought about clumping, things like that.
So you're preserving, electromagnetic U1 gauge invariance, but you don't care about the dark gauge invariance because you have
right,
that.
because I put an MA prime down, right?
Yeah, okay.
Yes, yeah. So there's various ways you can think about that. You can just say, oh yeah, the mass just exists. What are you going to do, right? Or you can say, oh, it's Higgs secretly, and the Higgs is what's giving it this mass. It's two different ways of thinking about it. I won't go into the details of which one is holier and things like that. That's not. Yeah, but you're absolutely right. Another thing to think about, which is again what excites me about this field, is particles are wave-like, and it's good to think about these particles as wave-like at these low masses. So let me contrast it with another regime which people are more used to, which is the particle-like regime for dark matter. So if someone asks you, hey, what's the most popular dark matter detector out there? Most people will answer something like, LZ, one of these xenon cousins, a big vat of xenon. What happens is a single particle comes in, scatters with xenon, causes some electron excitation, and out goes the outgoing particle. But notice the language, it's a single particle coming in, right? Now, what happens as you go to lower and lower masses? Remember, in this talk, I'm going to talk about roughly a milli-eV or so. You see rho dm, 0.3 GeV per centimeter cubed, can be written as 0.04 eV to the 4. So you see, as you go to lower and lower masses, there are many, many particles per de Broglie wavelength. As a result, this is a high occupation number state. At any point in this mass array, you can think of particles as either particles or waves. But it starts becoming more useful to think of these as waves as you go to smaller masses because of this high occupation number. For a vector, you can immediately talk about an electric field, right? We're talking about fields now. You can talk about an electric field, and then E is E naught cosine omega t minus kx. I've just written a free wave solution. Right? It's just a free wave, E naught cosine omega t minus kx. Now let's understand what these parameters are, right, that I've put in color. Omega is roughly is equal to the Hamiltonian, which is roughly Ma prime, which is the mass of this object. So this is what differentiates it from a regular photon, where here you'll be putting the energy of this particle, right? Instead we are putting the mass down. Now K is Ma prime times V virial because it's a momentum, right? Whereas for a standard model photon, these two parameters will be equal. For this dark photon, they are not. It's omega t minus kx, which is k is a much smaller number. It's 10 to the minus 3 smaller, which is V virial, roughly virial velocity around us, roughly 10 to the minus 3. So it's 10 to the minus 3 lower than omega. Okay? So for this reason, I will often be dropping k, this kx part of the term, part of this solution because of this suppression. The last thing I have to explain to you what this E naught is, right? Now, E naught square, we know is the total energy density, right, of this wave. So now let's equate E naught square to rho dm, but then let me put this, can everyone even see this? It's fine? Okay. Epsilon square rho dm, where epsilon square just suppresses this energy density, just so we understand in our frame how big is this electric field. Right? For electrons and protons looking at this electric field, how big is it? Remember, epsilon is this kinetic mixing parameter, epsilon ff prime. Okay? If you work it out, you see that it's an epsilon suppressed 100 volt per centimeter type electric field. So pretty large electric field if you did not put this epsilon in.
Sorry, the X is a space vector?
Space vector.
The X is just the kind of the space rotation? Is that direction?
Oh, X, yeah.
So it's basically three-dimensional, yeah?
Three-dimensional, yes.
So if you kind of neglect car, you kind of lose the kind of the dependence on the space, yeah?
Correct.
Okay.
Yes. But that, my point is that's a valid thing to do if you're sitting inside 1 over k.
Oh, I see.
Right? If your position is smaller than the typical momentum spread of this. Exactly. Good. Now, for detection purposes, the dark photon is not that different from axion-like particles, which you might have heard more talks about. Why is that? So again, I don't have to introduce axion-like particles to you. They're very popular. The axion itself is a solution to the strong CP problem. Things like that I'm sure you've heard about. But for the detection purposes, you have a dimension 5 operator that people typically invoke that looks like AFF dual, where F and F dual are both standard model photons, right? Standard model photon and its dual. A is the axion-like particle. Now, you can write this in terms of electric and magnetic fields. You see that it becomes A E dot B. Okay? In the presence of a large B field, dark matter produces an oscillating E field. Okay? This is the concept behind experiments like ADMX or DM radio. This is what they are. I think there's also a radio collaboration at Davis that does something similar. Right? If you want to look for axion-like particles, you put a large B field in, you maybe stick in an antenna or stick in an LC circuit, and you get out this electric field. Right? You can estimate again the electric field for this axion-like particle, and out comes an expression like this. In this case, you see the electric field depends on the static B field that you put in. Right? So you see what is becoming clear. The axion-like particle and the dark photon are cousins in terms of detection purposes because they are both producing oscillating E fields and B fields which you can go look at, right? So there seems to be a detection strategy coming out, which is both of these models are producing tiny standard model electric and magnetic fields. At a milli eV, let me estimate what it is. At a milli eV, roughly epsilon of 10 to the minus 8 is where the current limits are. Right? So for discovery purposes, if I put epsilon 10 to the minus 8, out comes a microvolt per centimeter. Okay? For the axion-like particle, out comes 10 to the minus 11 volt per centimeter. So it's clear if I'm going to build an experiment, go after the dark photon first, make improvements, and then go after the axion-like particle. That's typically how an experiment's life would work. Okay, for this reason, I'll be concentrating on the dark photon, but the hope is that we can eventually reach the axion-like particle parameters in this milli eV region. Notice that furthermore, this is not a DC electric field. It's oscillating at the frequency omega roughly Ma prime, mass of the dark photon. Which means that what you need to do is build devices sensitive to these tiny electric magnetic fields at the appropriate frequency. For this reason, there's been a proliferation of experiments at various different frequencies, all looking at the same dark matter model, but at different masses. Right? They're looking for either the axion-like particle or the dark photon, but at different masses. Let's look at some of these experiments. So let me start with the parameter space. On the y-axis, I'm plotting here epsilon, which is the kinetic mixing. If you can think about it, it's a placeholder for the cross-section if you're used to WIMP plots, right? It's telling you how strongly it couples to the standard model. On the x-axis is the dark photon mass. So it's going all the way down to like 10 to the minus 15, 16 eV even, and going all the way to 100 eV. So this is the parameter space. And this is the limit on the dark photon itself. Forget about dark matter. Just pure dark photon. You just put this new particle in your Lagrangian. Already there are limits on this dark photon, with no assumptions about dark matter. Once you put in dark matter as well, the dark photon dark matter can oscillate into standard model photons, and that will mess with the CMD. So there are some strong limits coming from cosmology. But these are some things you can maybe, with some perverse model building, get away with. So I've showed this in dashed lines, but worry not, I'll be looking at parameter space even below this blue line. Right? Just full disclosure of where these limits are. And in pink, I'm showing you the existing direct detection experiments. Okay? I'll go through them one by one, but what I want to point out is this glaring gap that exists between these series of experiments here and these series of experiments here. Right? Notice that, and then let's talk about why this is happening. Okay? It turns out that there is a blind spot, right, at roughly a millieV or so. To understand that, let's understand these two series of experiments. At lower frequencies, there are experiments like ADMX, Abracadabra, TM radio. There's a radio experiment at Davis as well, if I'm not wrong. And many of these experiments, what they're doing is they're building cavities, at least ADMX and its cousins, they're building cavities, and they're trying to make the size of the cavity match the frequency of this dark photon or axion. When that happens, this resonator builds up this electric field, and they can detect it. This is the concept behind ADMX. But notice that there is a sweet spot where you can take up this experimental strategy. Why? If you go to smaller frequencies, you have to build larger and larger resonators. Pretty fast, you either run out of room, or even before that, you can't build high Q cavities. Right? For that reason, people instead decided to put in, say, an antenna or LC circuits inside their cavities in order to resonate it with something else. So that's how these experiments work. At the largest masses, and of course ADMX will not work at higher frequencies as well, because you have to build smaller and smaller cavities, and at some point again you cannot build high Q cavities. Okay? At the largest masses, what people have instead proposed is using single photon detectors. So these are small electric and magnetic fields, right? You can think about them as single photons running around. So if you put in a single photon detector, you can do a bunch of experiments, but the single photon detector also does not work below 0.6, below roughly an EV or so. That's at the threshold of building successful single photon detectors, but people are trying to, it's an active area of research to push this to roughly a millieV or so. Okay? It's too high in energy for high Q cavities, this millieV region. It's too low in energy for single photon detection. I don't want you to think that there are no proposals in this parameter space. What people are doing instead is they are using broadband bolometers. So they're just sophisticated thermometers, if you want. They just stick it in and they ask, hey, is there a little bit of heat coming from some source? I don't know what it would be, but you might realize that very soon it's not a very good discovery tool, just sticking a thermometer somewhere, right? So it would be nice if you could build a resonant detection scheme, right? So the question I want to ask and answer in this talk is there a resonance scheme at roughly a millieV or so?
You're saying for the broadband search, they can only know there is a signal, but they don't know the mass of that.
Exactly.
Okay.
And furthermore, once they see that noise, there is not many things you can do, because that noise is just going to exist. Whereas if you build a resonant device, you can zoom in, and the dark matter signal is pretty narrow.
Yes.
So it's good to build a narrow band thing that matches that bandwidth.
Okay, good to know. Thank you.
Okay. So in this context, I would like to introduce you to electron traps. But I also want to, talk about a very broad synergy here, which I want to tell you about, and that exists between quantum information science on one side and dark matter detection, which I've been trying to talk to you about. And that's the following, right? On the side of quantum information science, you might know this by now, is that they are trying to realize qubits to build a computer, right? And the thing I've been thinking about is this: can these qubits be used as a dark matter target? Right? This is what I've been trying to understand, right? They do single quantum readout. They would like to understand, are they at the 0 or are they at the 1, right? I want to ask the question, could this be the dark matter signal readout? Furthermore, quantum information scientists trying to build these qubits, amorphosicists, they are trying to lower their backgrounds to maintain entanglement for longer. Right? And the question is, does this mean that they are by themselves creating low backgrounds for a dark matter detection? And they're trying to scale towards large n qubits so that they can realize a quantum computer that's powerful enough. Right? If I've convinced you that these qubits are really dark matter targets, notice what they are doing. They are trying to scale this dark matter detection experiment. In some sense, so if the first 2 points hold, then you could just piggyback on these amorphosicists doing quantum information science, and they're building for free better and better dark matter detector for you. Right? And this is what I want to explore for the rest of this talk. Okay. Let me give you an example. So let's step back. What do we want to do? We want to build a 2-level system at roughly a milli-EV, and in AMO language, that's roughly 100 gigahertz or so. Okay? Going down, what are some 2-level systems we have seen? At a few EV, it's things like ionization. This is what xenon works in. It's not really a 2-level system, but I put this in this place anyway. At roughly an EV or so, you have things like semiconductor band gap or quantum dots, which I worked on, which are themselves also possible quantum information science devices. Roughly 10 milli EV or so, you have things like rho vibration and molecules, some other condensed matter systems you can think about. But till I worked on this, I did not know of resonance systems at roughly a milli EV or so or below. Right? But let me show you an observation, right? And this is what, in some sense, holds the rest of the first part of this talk together, which is that if you put an electron in a large stable magnetic field, say roughly 5 Tesla or so. Okay? It's a very simple system, right? But out comes a frequency. What is that? That's just the Landau level, right? It's just cyclotron orbits. And you can ask, hey, what is this energy? And out comes 150 gigahertz. This is exciting. This is exactly what we were looking for. So what this is saying is that electrons trapped in a strong magnetic field exhibit cyclotron orbits. And when you quantize it, that's just Landau levels for you. The question is this a resonant detector for a dark photon? That's what I want to ask. Furthermore, a priori, I do not know where the dark photon mass sits. It's not at exactly 150 gigahertz. It could be at 135.9 gigahertz. So I need to be able to scan in order to access a lot of this parameter space. And how does ADMX do this? They put a rod or some kind of mechanical object in and then move it around. So it's a very difficult enterprise for an experiment like ADMX to actually scan, and that is the reason why they're in a very narrow frequency window, right? They have to just build a new resonator or fill their resonator with some substance, something like that, in order to be able to scan. But here, scanning is a little more straightforward. All you need to do is just scan this magnetic field, and if you scan this magnetic field, your frequency changes. It's just proportional to B. So if you just scan B, you're scanning the frequency, and your narrowband detection soon starts exploring new parameter space. Okay? The final question, of course, is it possible to detect a single jump? Right? There are probably hundreds of different objects out there that can do this. My body's probably absorbing, microwave photons, right? I mean, you cook food, there's microwave photons being absorbed by your food. Doesn't make it a good dark photon, dark matter detector, right? In order to understand this, let's understand what this electron trapped object looks like, right? What they are, so it turns out trapping these single electrons and single ions is such a difficult topic that the discovery of these, or the invention of these traps won 2 Nobel Prizes, one for the Penning trap and one for the Paul trap. I'll explain the Penning trap here. These are local minima, right, in all 3 directions. And the trapping is achieved in one direction by the axial magnetic field, that's Z, right? In XY direction by the Z magnetic field. Notice that it's moving in a circle, which means that it's not drifting away. But if you just leave it in the single magnetic field, it can drift either up or down, right? You need to arrest that, or your electron will just be gone. For that, they include what are called quadrupole electric fields that take care of trapping it in the Z direction. Okay? So you have trapped it in all 3 directions, and you have roughly 3 harmonic oscillators for this reason, and they are called the axial motion, which is this way, the cyclotron motion, which is these small circles, and it turns out that because of a drift, the cyclotron center is itself drifting along a circle, and that's called a magnetron motion. It's a very low frequency object, so it takes a really long time to make this circle. It's very slow. So this is roughly what a penning trap is, 3 harmonic oscillators, and the question we are asking is the cyclotron orbit I just showed you before, can I discover a single jump in that cyclotron orbit?
Sorry.
Yeah.
Is the experiment related to that one? Is it still in room temperature or no longer? Is it in a curtain?
I'll tell you in a second.
Okay.
Yeah, great question. If you remember your quantum 101, you will realize that if you have a disturbance like this, a dark photon coming in, only delta n equals 1 transition allowed because of selection rules, right? You have sensitivity to tiny electric fields, so you can ask how tiny. So you can compute the rate that's just given by the electric fields that we put in earlier, and out comes 5 every 10 seconds for this epsilon 10 to the minus 8 number I was describing to you before as the cusp of discovery. That's what's not ruled out yet, right? This is very promising. It satisfies one other condition for a dark matter detector, which is that it should happen within your lifetime, right? And it is well within our lifetime, 5 every 10 seconds. So this seems positive news. And the question still remains, can I do this single jump from here to here, right? So when we realized this, we talked to Jerry Gabriel. He's one of the pioneers of electron trap trapping. And what he told us was the following, okay? Not only could he do this, he could do this 20 years ago, in 1999. Okay? He showed us this from one of these plots. He can do quantum non-demolition measurements of the electron cyclotron state. That's possible, so he keeps it at the ground state. And you see, if there is a jump, he can differentiate between the 1 here and the 0 here. So that's possible 20 years ago. In fact, 0 to 1 and sometimes 1 to 2 happens, and then there's a natural decay going down. You can ask, hey, what is causing these excitations, right? That's the answer to your question, which is the wall is causing this. The wall is at 4.2 Kelvin. Black body radiation from the wall is playing with this electron. That's what's shown here. A single electron. Okay? With 1 second observation time, you can differentiate the 0 from the 1 from the 2. Furthermore, as he cools, you see that the number of jumps is lower. I found this really cool that they can do things like this, right? A single electron, and then they can observe it, and they can observe this black body radiation from the walls. Furthermore, if they keep cooling, below roughly 0.1 Kelvin or so they have cooled, they do not observe a single jump. Right? That's also obvious. Black body radiation reduces as you reduce the temperature, and at some point you do not have any jumps anymore. So this is showing us 2 things. One, that such an observation is possible. And number 2, if it happens, it's possible. And number 2, they can create a background-free environment by cooling to sufficiently low temperature. So this is for 1 hour, right? What they told us was they can trap electrons for years. It's crazy. Like they can trap it for so long that sometimes they name their ions. Like this, the calcium ion that they have is a name. Sometimes these PIs, they know their ion for longer than they know some of their grad students. Right? That's a single ion. Like this is crazy to me that such things exist. Our AMO colleagues have been able to do these amazing things.
Yeah, but they all look the same, right?
Right?
They all look the same, though.
They all look the same. It's true. Someone say about that when they're grad students, but yeah, I digress. So here's their apparatus. So what they are doing, the Gabrielsi group at Northwestern, what they're doing is not just trapping the electron for fun, but they're trying to measure the electrons G-2. So there's a lot of hype around muon G-2 right now, right? But the electron G-2 was measured, it's an older measurement in some sense, right? And it's measured to exquisite precision, and a device like this was also one of the world-leading measurements of the fine structure alpha, for example, things like this. Lots of cool physics coming out of a device like this. Anyway, this particular device is measuring the electron G-2, but notice that it's in a complicated object. It's in some sense a cylindrical cavity, right? It's not in free space like I pretended it was till now. So it becomes a little more complicated problem trying to solve this. So let's understand the effect of a metal plate like this. So that's what we're going to do next. Okay. So let's start with the plate. So there's a metal plate. It's in some sense dipped in dark matter. Dark matter is everywhere. And so there is a parallel component. Let's say it's all parallel just for argument's sake. E dark parallel is epsilon square root of rho dm, right? That just came from E square has to be the entire dark matter density. Right? Now I'm going to tell you what the consequence of something like this is. There are electrons in this metal, right? What do we learn from electromagnetism 101? That parallel electric fields cannot survive in a metal plate. So the electrons are going to try to, conspire to destroy this electric field. What do they have? What do the electrons have at their disposal? They have plane waves, standard model waves, right? What they're going to do is produce these plane waves that exactly cancel this dark parallel electric field, right? But notice that now omega is k because these are standard model plane waves. These are not dark matter waves. They do not have a mass. So what's going to happen is that at x equals 0, this field and this field are going to cancel. But everywhere else x not equal to 0, you're going to create a new field. So what you're learning is that a metal plate kept in a dark matter density is acting as a laser in some sense. It's producing these standard model waves. Okay? So what would happen if I instead consider a cylinder, which is what I have at hand? What would happen is the cylinder will instead of producing plane waves, is going to produce cylindrical waves. Okay? These cylindrical waves have the property that they're going to focus at the center. Okay? So usually, if you do not consider your backgrounds properly, you will usually be a worse off experiment. But in this example, you're actually a better experiment by considering your backgrounds properly. For free, we got a focuser, an electric field focuser, a dark matter electric field focuser out of this cylinder. Right? If you do not like my hand-wavy explanation of the cylinder, what you can do is the following. You have a boundary conditions, and this is an electromagnetism problem, which is you have boundary conditions, you have a source current provided by dark matter, you can go and calculate what the electric field is everywhere. And you will get the same thing. So this kappa, defined as E cavity over E free, right? It roughly goes as square root of mr, where m is the dark matter mass and r is the cylinder radius. Right? It will be practically useful, this focusing effect, when mr is much greater than 1. The existing cylinder that they have has mr of roughly 14. So it's somewhat useful, but not, it's not crazy useful because they have the cylinder. So in the second iteration of our experiment, what we plan to do is to use a sphere instead, because that will produce spherical waves, which will concentrate at this point. So that will have, in some sense, linear focusing in field or quadratic focusing in the power, mr squared. That makes sense? So this is what we want to do in our future. So this is the Gabriel T group. Jerry is right here, and his student Xing Fang led this experiment, and they took some data. They took 180 hours worth of data at one single frequency. Okay? They didn't see anything, otherwise you would have heard it in the press. So there's some very strong limits coming your way at a narrow frequency band, of course, and that's what's shown here. So this 180 hours worth of data at a single frequency set some really nice limits, roughly 2 orders of magnitude better than the existing limits from xenon 1 ton in this narrow frequency window. Okay. There was no scanning done. Like, remember, I advertised this as a very easy scanner, but it turns out that the magnetic field scanning needs some refrigerants, which they do not possess because of the supply chain issues. So this is something we plan to do for the future. But nonetheless, this experiment in this narrow frequency window acts as a proof of principle and also demonstrates that over 180 hours, there is no background. They did not observe a single background event. Okay? So this is what we plan to do in the future. Scanning 15 seconds per bin. Bigger cavities. So we want to go roughly to 2.5 centimeters. So these are all very modest goals for us. And very straightforward. Instead of 1 electron, we want to put 10 electrons in there. And even explore things like, can we trap it at a higher excited state, which has an even higher dipole moment, things like that. So with these modest improvements, we can easily reach this parameter space. So 1 order of magnitude in mass, which is really difficult to reach. So this is where we are right now. This is the red line, a very narrow frequency range. But scanning is what we plan to do in the future, and we'll get 1 order of magnitude improvement over xenon 110 if we run this for a year. This is in some sense almost out of the box, things they can do today. Right? In the future, we want to think about things like this. Let's say instead of a sphere, you had a parabolic mirror and a cylindrical trap. You might have heard of the bread experiments, which uses a geometry like this. What they're doing is, now these cylindrical waves, because of this parabolic mirror, focus these waves to this point here. That's what's shown in this graph. So what you might have realized, what I'm proposing to you, this electron trap, is essentially a really, really good electric field sensor or a photon detector. Right? So if you put your electron trap here, you could use the breadth setup, and you will have a narrowband frequency readout mechanism. So this is again something we're exploring, like maybe move the focus even outside this so that a trap could just exist here, things like that. So stay tuned, like these are not set in stone yet, these ideas. One last thing we're exploring, you might have heard of various Axion talks, things like Abra. In the Boston University, they're doing another such Axion detection. This goes down all the way to roughly 10 to the minus 10 eV or so. But I'm going to show in the next part of my talk, there are ions. You can replace electrons with ions, and you can go to even lower frequencies, right? So we're talking about 10 to the minus 11 or 10 pico eV, and this is something ion trappers can detect. Single jumps of 10 pico eV or 1 pico eV or so, right? So we are currently in the process of exploring whether such technology could be used for Axion detection in this case. So we talked about dark photons in the first part of the talk, and in the future we are trying to see if Axion detection is possible at frequencies much lower than anyone has ever gone to for Axion-like particle detection. So this in some sense is what I've done in the first part of the talk. Let me summarize. Photon Dark Matter is a very promising model. It's hard to probe in the hundreds of gigahertz range. We proposed a new way to detect this, which is using existing apparatus, built for entirely different purposes, but it turns out that it's an ideal place to look for it, right? It was used for electron G-2 measurements. It used a single trapped electron. In some sense, this is the most ridiculous dark matter detector out there, right? You're talking about typically Avogadro number of atoms. This, in some sense, takes the smallest particle which we are capable of trapping, a single particle, and it shows that a single particle could still act as a dark matter detector. It showed sensitivity to new parameter space. This I think is really cool. A pilot run was conducted at a single frequency, and it observed no events over 180 hours. So a really long time for no backgrounds, and still a null background detector. And we are doing things like scanning and other improvements, which are stay tuned for these updates.
So when did the result publish for this pilot run?
Last year.
Last year, okay.
I don't remember the month. But yeah.
Last year is fine.
Right. Yeah. How much time do I have? Yeah, 20 minutes. Perfect. So yeah, let me move to the second part of my talk. This is Millicharged relics. Okay. And in some sense, this is a philosophical question I've wondered about, which is the following. As a community, as particle theorists, when we think about dark matter and its phenomenology, right, what we ask is, hey, what's a good stable particle that has the correct properties to explain dark matter? Does it set the correct relic density, right? What I want to ask in this part of the talk is it still an interesting question to go the opposite direction, which is your theory might have a stable particle, right? Your theory might have a stable particle. Your theory was written on for entirely different purposes, not for explaining dark matter. But then could that stable particle just exist in cosmology? Cosmology was just kind enough to us to produce these particles. Could I look for them as dark relics? I think it's still an important question to go in this opposite direction. There are many well-motivated examples of this. I know John, for example, has thought about things like monopoles, right? There are other examples, things like axions. There are other quarks or heavy quarks, all kinds of colored objects. People have talked about things like this. Do they form exotic bound states on Earth? Can we go look for them in heavy water searches? These are things people thought about 10, 20, maybe 30 years ago, right? In this talk, I'll talk about millicharged particles for the same reason, right? They might have robust predictions for the relic fraction FDM much smaller than 1, where FDM I'm defining as what fraction of dark matter does it make up, right? It could be much smaller than 1. Does that mean we should throw it away? Not interesting. I don't think so, because let's say these particles were much heavier than a TeV, or had coupling much smaller than 1. What other way do we have to look for these things? It's possible that another collider doesn't get built in our lifetimes, right? I mean, that would be very sad, but it is possible that happens. And this might be our only way to go after these particles, which is, depend on the mercy of cosmology to produce these things for us. Another example is the cosmic neutrino background. Sure, it doesn't make up all of dark matter. We have known this for decades now. Nonetheless, it's still something that would be very cool to see, to go after this background, learn about the early universe. There might be information about the early universe that's sitting in these relics, and we could uncover them that way, right? These relics have also been invoked to explain some recent anomalies seen in experiments, right? And the cool part is that you can reuse the same direct detection concept that Witten and some other people taught us, which is look up at the sky. These things are already there. You don't need to produce them in a collider. Just look up at the sky and they will just show up in your detector if the properties are correct. Right? So that's what I want to do now. Right? So specifically to millicharged particles. So what are these? These are particles with tiny electric charge. So epsilon now is how much smaller than an electron is this charge. So pardon me for reusing this epsilon from the first part of the talk. But epsilon is in some sense what's called a millicharge. Again, please don't get confused with this milli adage, right? That's not 10 to the minus 3, you just stuck with it. I mean, it's not my fault, like people did this in the past. So I will not be thinking about epsilon 10 to the minus 3, okay? These are simple models to write, either with or without a dark photon, right? So you can think of either a direct millicharge or it's charged under a dark photon, and the dark photon kinetically mixes with the standard model, and this kinetic mixing produces an effective millicharge. So these are in sometimes two iterations of the same phenomenology, which is you have millicharged particles. And if you discover this, you could, start asking questions about charge quantization. Like in the case without a dark photon, hey, why is the electron 1052 the charge of a unit charge? Like things like this might arise if we do discover these millicharged particles. Furthermore, they can easily be made stable, right? These are millicharged particles, so this object has a charge, so you can make this, it's very easy, it's an easy model building exercise to make this object stable. And the question is, it's stable, does a relic density exist? Is there some non-trivial amount of, an irreducible amount of it around the Earth today, right? It's looked for in various experiments. In fact, the LHC is building almost a dedicated experiment called Millikan, specifically for millicharged particles. Okay? And there's been recent resurgence, lots of papers written down because of what's called the edges anomaly, a 21 centimeter anomaly, which itself is, it was short-lived, it went away, but there's been some rich literature considering these particles because of the edges anomaly.
Is it a milli-Q starting to taking data?
I'm not sure.
I can answer that. I work on Millikan.
Okay.
Oh, okay, perfect.
Yes.
Yes.
Yes, we're taking data with run through now. Run through the LHC for 2023 is about to start. So.
Okay. So,
Awesome.
don't know when will you have published the result?
Aim is for the end of the year.
End of this year. Okay, good.
So there's actually, I should have known this because there's some Millikan plot right here.
Okay.
See, this is green, right? So here's another interesting thing, right? Let's say a layperson comes and asks you, hey, why haven't we seen any new physics yet, right? What you tell them is, hey, either new physics is at very high masses, we have not built strong enough, colliders, any instruments that can go look at that energy range, or it's too low in coupling, such that we've not had enough luminosity to produce these things, right? This is what is typically thought of. But here's a very simple model we can all understand, millicharged particles, right? And notice this parameter space, right? Here, the mass is roughly a few GeV. I mean, that's older than my age in terms of when we could build these colliders, which could reach a few GeV, right? And the charge can be 0.2. This is crazy to me, that this parameter space is still open. And we talk about the isolated standard model, that stuff is like really, really far away, and it's going to be impossible to go look at this parameter space, right? And here it is laughing at us, like, this is a really large charge, right? And I want to see if I can go after this parameter space, right? Not necessarily this, but you know, this. I mean, here it's actually millicharged, right? To maximally confuse you, 10 to the minus 3 charge roughly at a GeV or so is not ruled out yet.
So is this particle is a boson or is a fermion?
Let's say fermion.
If with the boson, is those things still okay at a 10 GeV at a 0.2 charge?
Why? What will happen?
I mean, there's no bound from lab.
There
This
is
is
a
the
bound,
lab
that
bound.
is the bound.
Even for scalar, bound the same.
I would think so,
It's
yeah.
not gonna change very much.
Yeah.
It's not gonna change
For
by
vector.
orders of magnitude,
Right.
right? It'll be a
Okay.
factor of a few.
Okay, this is so large. I mean, can it be pair produced at the lab?
Could be. I mean,
10
again,
GeV.
These are all things they've thought about, right? And those,
Yeah,
all those
yeah.
limits are in this plot.
Still,
Right.
okay, still very large.
It's
I would be
stunning.
surprised
Yeah,
that
it's
it's so large.
a joke, right?
Yeah, I thought there were these, you know, I mean, there were these E plus E minus machines that were in a few GeV range, right?
Yeah.
So they would have produced these things just above threshold, and you're saying they wouldn't have seen
Yeah.
the tracks or something?
Right.
Because there
Or-
was that,
yeah.
maybe you know.
Yeah, even
Why
for
is it so
CMS,
hard?
it's really hard because all the electronics are optimized to see things that are Q equals 1. And once it just, once you go down to 0.1, that's 100 lower energy deposition, and it's just lost in the noise.
What about that hadron collider? What
So
about
it's
the
noise.
But it's still
No,
The
it's
same.
detector.
It's just
the
detector. So you're saying
It's
that
the same.
it's in the
Okay.
noise of the energy deposition is just too little, so you just don't
Yeah.
see them.
And for CMS, you can only get to about 0.2 maybe in
0.2.
charge.
Okay.
for 10 GeV?
Well, for anything, below that it just doesn't deposit enough energy. I mean,
Oh,
you
okay,
could get,
okay, okay.
if you have a huge cross section,
So
maybe. we
Millikan
can
is,
lost it.
Millikan is right there.
So yeah,
Are you gonna push?
And Millikan's
To be
going to be
fair-
better.
this is a
Yeah,
demonstrator for Millikan. That limit there was like a very small version of
Yeah, yeah,
Millikan,
yeah.
which is why it's less.
That's
But
what I'm asking.
Millikan is going to push to basically half the Z mass, and about 0.1 at half the Z mass.
At 0.1, but it's still, okay,
At half the Z mass, and it goes down to
Yeah.
10 to the minus 3 or so.
all right.
Okay. So I'm going to show you another way to look at this parameter space. Okay. What I would call a very delayed collider. You'll understand why I'm saying that. Okay? So this is something I pointed out with Maxime and Co., which is he had pointed out earlier that mesons are produced in cosmic rays. I mean, that's not something he pointed out. It's been known. That's kind of how we discovered mesons, right?
But it's in the forefront of the minds of Russians.
Yes, correct.
Somehow.
Right. But notice that neutral mesons decay to E plus E minus pairs. And if there are millicharged particles, then they can be decaying to millicharged particles, right? To QQ bar pairs, right? What this means is that there is an irreducible flux on Earth. Forget about dark matter, forget about cosmology, right? You're producing for yourself an irreducible flux, right? Let's compare fluxes. It's very small. This is a virialized dark matter flux at 200 capital MeV or so. Epsilon of roughly 10 to the minus 3. This is actually millicharged. You see that the amount produced from meson decays is a few orders of magnitude smaller. So this is roughly 10 to the 4 in these units. This is roughly 10 to the minus 11 or minus 12 in these units, right? So it's 16 orders of magnitude lower, but it's irreducible. Right? So let's explore, hey, is this something that's maybe something
So
detectable?
what do you mean by irreducible?
If I put this millicharged particle in my Lagrangian, there is no way to turn
Okay,
this
yeah,
off.
Right.
You can't play with cosmology.
Right.
You can't say, hey, low reheat temperature, that's why I don't see these
Sure, sure.
particles, right? You're stuck with this. It's almost like a collider in that way. In that if you turn on a collider, you would see these things, right? You would produce these things. Let's now trace what happens to these particles. They have high boost, right? After all, they're produced from meson decays. So they are roughly at a GeV in terms of energy. So this high boost makes them penetrate deep down into the Earth. What do we know about Rutherford scattering? As you slow down a particle, it enhances in cross-section, right? Because it's a 1 over v to the 4 type cross-section. This enhanced cross-section makes it have tiny mean-free paths, roughly a micron or so, once it slows down. Which means that it's just, struggling to get out of the Earth if it wants to evaporate. Okay? But nonetheless, we are stuck. I mean, it's almost a cruel joke. all the mesons are roughly few GeV or lower, which means that all the millicharged particles you're going to produce are roughly GeV or lower. What do we know about GeV? That's the mass of hydrogen which evaporates from the Earth, right? So these millicharged particles, while still struggling to get out, are going to escape from the Earth. It would be nice if they just, stuck to the Earth, right? Is there a way to do that? It turns out that the Earth helps you out, right? Think about you might have seen this in Feynman lectures, which is again another stunning fact number 2 or 3 in this talk, if you will, which is that there is a near constant electric field between the Earth and the ionosphere. How big is it? It's roughly a megavolt. It's a huge electric field. Okay? Furthermore, its electric field is roughly 100 volt per meter, right? So let's approximate me as 2 meters, okay? The potential difference, if I were not a good enough conductor, the potential difference would be 200 volt, enough to charge my laptop. Except I would be a very shitty battery, such that the charge would end really fast. That's why this doesn't happen. Okay? Nonetheless, this electric field exists, right? And you might have already realized what I'm going to say. If pure milli-charge, these charges feel the Earth electric field, and as a result, one-sign charges cannot escape the Earth. They get accumulated for the age of the Earth, right? So the Earth then sometimes is going around making its own milli-charged particles when it sees cosmic rays, and it has a way to bottle it up on Earth.
So sorry, for this Earth, the electric field is pointed towards the Earth or towards the sky?
Depends on the charge, right? One charge points towards the Earth.
Let's say if the charge is positive.
Positive charge remain on Earth, negative charge escape the Earth.
Okay.
So the point of the milli-charge evaporating, you said something about hydrogen. Is that just because the numbers work out to be roughly the same as hydrogen, and we know that hydrogen evaporates?
Exactly.
That was just a quick
just
shortcut.
The quick shot, yeah, exactly. And the number comes from 300 Kelvin, what's the thermal velocity?
Yeah.
Larger mass, smaller velocity, so larger masses, and that velocity shouldn't be larger than the Earth escape velocity.
Okay. All right. Thanks.
Right. But notice that now there's accumulation over 5 billion years, roughly how long the Earth has lived, right? Like there have been cosmic rays for as long, there has been an atmosphere but for almost as long, and it turns out they know that the electric field has existed for as long, because there are thunderstorms which create these electric fields for that long. Right? Now you can ask, what is the effective number density as a result? And you will see that around this parameter space, which is just about unexplored, it's roughly 10 per centimeter cube. And as you go to smaller charge, you can go to say 10 to the minus 3, 10 to the minus 4, 10 to the minus 5 per centimeter cube. Right? So the flux was tiny, but because of this accumulation effect, you have near dark matter amount of charges sitting around Earth.
And you expect that these things are somehow uniformly distributed down in some density?
If they are small enough in mass, they are uniformly dense. Right. If they are dense, then they sink towards the core of the Earth. But you can show that if they are large enough in mass, they just uniformly distributed all over the Earth, but in the rock. They don't seep into the atmosphere because of this electric field.
So if you pick up a piece of rock from a mine,
Right.
it should have roughly this density.
Exactly.
It shouldn't be.
Right.
Okay. Because they're just sort of diffusing.
Brownian motion.
They're just diffusing through
yes.
the. Okay.
Yes. Exactly. Right. So this I showed with Maxime that this crazy number density exists on Earth. How would you look for it? Right. Let me skip this. I'm showing that the same thing happens to dark matter as well. Right. After all, these cosmic rays are in some sense special dark matter, an irreducible dark matter, if you will. But let's skip this. But let me point out that, hey, the number densities are so large, the cross sections are so large, why aren't we seeing these things, right? That is because the energy deposit is room temperature, 300 Kelvin or 26 millieV. And we have not built many detectors that can do 26 millieV. Furthermore, in the first part of the talk, I showed you something that can do this, right? After all, it went to a millieV, but not so fast. Remember, if I built a low threshold detector, like the question you asked, I had to build low temperature walls to surround this detector, right? Right? Now, if this guy has a very small mean free path, then it's going to immediately thermalize in this wall, so I have to build really, really, really thin walls to be able to do this. right? Or it's going to immediately thermalize, and by the time it hits the detector, it's going to be at the colder temperature, such that, I can't do anything. Right? So for a long time, I thought this was dead because of this effect. Till I found this new toy I'm going to tell you. So just to put things in perspective, an electron trap would have worked. After all, it had 500 mu eV threshold, but its walls were at 10 mu eV in order to not get fried by black body radiation. Right? How could you possibly have higher temperature walls and a low temperature detector? That's the next question I want to answer. Right? So let me introduce to you ion traps. Right? This is a very simple modification. I'm just taking the electron out and putting a proton in. Same magnetic field, same cyclotron orbits, but out comes 60 nano eV, right? Just because this is 2,000 times heavier, the proton compared to the electron, right? And this gives me a millikelvin, right? Then you can ask, oh, it's a millikelvin, great. The first part of the question is answered. This is much smaller than 300 Kelvin. I should be able to detect, but you could ask, hey, don't we have to cool the walls to much less than a millikelvin to not fry this ion, right? And if you know your experimental physics well, you might realize that this is a really, really, really hard thing to do, right? Going below a millikelvin, right? You could ask, what do ion traps work in? They work at room temperature. This is insane, right? They can detect millikelvins, but they're not fried like black body from the walls, which are at 300 Kelvin. Why is that? It's because, again, this ion is an approximate harmonic oscillator, right? And there is selection rules for black body radiation. Delta N only plus or minus 1. So it absorbs an extremely narrow band of this black body radiation. That's the first point, okay? An extremely narrow band. The second point is the wavelength of this black body radiation is now much larger than the cavity. Remember, earlier we worked in MR equals 14 limit, but we have reduced the M 1,000 times smaller. We have kept the radius also smaller. So MR has reduced by a lot, mass times radius. Which means that these are super cavity modes. So these modes never get generated to begin with. They don't have support inside the boundary conditions of this cavity. For this reason, there is good thermal insulation between the ion sitting here and the walls sitting here, just purely because of quantum mechanics. Okay? Furthermore, the number of photons with energy omega is much smaller than T is negligible, and yeah, of course not supported, and for this reason, this is happy to live in a 300 Kelvin trap. And when I first heard it, this is completely bonkers to me. Nonetheless, you can scatter with a Millicharged particle, and remember, scattering does not have selection rules. Why? The momentum transfer is very different for scattering compared to absorption or emission. Right? As a result, the momentum transfer is much larger than the energy transfer, so you break this selection rule barrier, if you want to call it that. And as a result, there's a new source of heat from the walls into the ions. Right? So if an ion trapper were trapping ions for building a quantum computer, and these millicharges existed, they would be a nuisance to these trappers. In some of the part of the parameters where I'm going to show you, they would have already seen it because they wouldn't have been successful in building
What is the frequency associated with this energy difference? What are these transitions?
megahertz.
Megahertz. So So you don't have to. Do you have to worry about I don't know, shielding from radio or something like that? I mean, so somehow in position space you're okay because the wavelength is very long, right? But in frequency space, I would think that if you were to, don't you have to worry about time dependence of megahertz level?
Right. So these cavities are decently high quality, such that they reject any radio coming from the outside.
So they're just shielded.
Right.
From
So nonetheless, there is a non-trivial heat source, heating rate I'm going to show you. It's not like the electron trap, which is zero events. There is some non-trivial rate. Okay. So there are two observables that you can look for. One is called the heating rate. What you do is put your trap today, go home, come back, you measure it 1 day from now, and ask, hey, what is the differential heating rate, right? Let's say it is 10, it has jumped 10 quanta. You do not know if it was a single jump of 10 quanta or 10 jump of 1 quanta. We don't know that, but nonetheless, that's an observable. If you do not, if dark matter predicts a jump of 20 quanta, that dark matter is ruled out from the observation of a jump of 10 quanta. Okay, that's the heating rate observable. The event rate observable is more nuanced. You have a high cadence measurement. You just keep measuring every few seconds or so. So you can differentiate between 10 one jump and 1 10 jump. Okay? And furthermore, if you observe a single, say, 5 jump, it turns out that no standard model process can do this. There are standard model processes that do this. Funnily enough, it's called anomalous heating because they don't fully understand what causes it. They think it's from the electrodes. But nonetheless, they have never ever observed a single 5 jump event. Why? Their pressures are at roughly 10 to the minus 8 millibar or so, 10 to the minus 18 millibar or so. They have exquisite vacuum inside these devices, such that they will not see a single 5 jump event. Okay, and if they are able to do this event rate, which they have not done it quite yet, then you see only dark matter can do this. You will have a background free dark matter or Millicharged particle detector.
So can you go back one slide?
Yeah.
Or maybe another one. Oh yeah, no, that one.
Yeah.
Next one. So the selection rules for photon absorption only plus or minus 1.
Yeah.
But dark matter can do more than 1 at
Yeah.
time? Okay, that's the
Why? Because scattering breaks the selection rule.
point. Okay, oh, I missed that point.
Right. Maybe I went too fast through it. But yes. Okay. Scattering breaks the selection rule, so you can do this. So heating rate is something they already observed. So I miss, 10 to the minus 18 millibar or 10 to the minus 21 bar is where they are at. The work function of metals prevents electron evaporation. So in some sense, it provides a natural sieve, this work function, to allow only Millicharged particles and prevents tandem model particles from flowing and flooding this cavity. The lowest measured heating rates are roughly 10 to the minus 12 eV per second. And the black body estimate, despite all the suppressions I told you, comes to around 10 to the minus 14. The background gas estimate is even smaller at roughly 10 to the minus 60 eV per second. And this is expected to be from electrode noise. So notice, I mean, you might think this is some kind of esoteric science, right? Like some couple of people doing this. No. Like each one of these is a data point on heating rates coming from this really burgeoning field of quantum information science. Remember, this is very important to them to trap these ions. And you see how much work goes into this. So this is itself from 2014, right? You can only imagine what it looks like today. Right? And what are these? Like in the x-axis is the size of the trap. Let's not concern ourselves with that. But the y-axis is the heating rate. And what is at the CERN experiment have reached the lowest. They can reach roughly 10 to the minus 3 quanta per second. That's the kind of heating rate that the lowest heating rate that they have observed. So we collaborated with these experimentalists, right? And let me just show you this. So remember, this is the permanent accumulation. So we are roughly 10 to the minus 1 to 10 to the minus 3 per centimeter cube. We are not there just yet, okay? But the existing experiments, we did not do a single dedicated experiment yet. Just reinterpretation of the heating results that have already been seen already sets limits in this parameter space. So here the lab density is 1,000 per centimeter cube, so it's 1,000 more than what I would like, but here, that's where we are today. But just borrowing the heating results from these other collaborations, you set a new limit in this parameter space. Okay? The y-axis is the charge of the millicharge, and x-axis is the mass of this millicharged particle. And you see that some of this parameter space is ruled out for 10 to the 3 per centimeter cube. If you did this experiment 1,000 times better, then this would absolutely be new parameter space you're ruling out, because there's a robust way to produce these millicharged particles. We are not there just yet.
Sorry, so what does it mean? What's the 10 to the third per centimeter cube?
Right.
I thought there was a prediction.
There's a prediction
what the
for
density is. So this is.
Right.
Oh, and it just depends on the
charge.
Right. Okay.
Right.
So this corresponds to large charge.
So this corresponds to, in some sense, nothing.
Yeah.
Right.
Something that's already
Right. You could say this corresponds to, say, very, very small subcomponent dark matter.
It's ruled out, but not by actually seeing it that density in the lab.
Right.
It's ruled out by other things.
Oh no. This is still a brand new limit. it just doesn't correspond to the irreducible. I'm setting some very high standards here in terms of like, I'll only look at the irreducible. If you relax your standards a little bit, there are other sources
This
of
is a
Millicharged.
bound on stuff that has that density for reasons
Exactly.
that we don't know.
I can
Could
tell
be
you
some cosmic background.
exactly.
Got
Some
it.
dark matter,
Yeah, yeah,
let's say 10 to the minus 16 of all of dark matter is in Millicharged particles, you would rule it out.
Okay, I got it.
Let me just compare it to what is available previously. That is from optical levitation. They took small pellets, put it in electric fields and oscillated them. That was the best limit on Millicharged particles. That came out to around 10 to the 8 per centimeter cube. Okay? So by not doing a single experiment and just piggybacking on someone else, we have reduced that by 8 orders of magnitude. Okay? In this parameter space, in this parameter window, and then we are of course exploring other parameters. Okay? So what we're doing next is with the base group, we are implementing single event rates, right? Because once you observe a heating rate, there's no point, prolonging it. Like when you observe the heating rate in 10 minutes, you're going to observe the same heating rate in a few hours or a few days, right? There's no point going in that direction unless they find ways to improve their heating rates. But what you can do is single event rates, which are a background-free channel. So that's something we're exploring. We're exploring excitations and ion lattices, right? So take many ions, many ions, right? The heating rate from the background will heat all of these together, these ions together. It'll, in some sense, heat the center of mass mode. But you can look at internal modes, so this is something we're exploring with the group at Duke, where these internal modes are only heated by Millicharged particles. So that's something we're exploring. And then finally, you can take lessons from Earth and build yourself a bottle. The Earth, remember, is a spherical capacitor. So you could build yourself a spherical capacitor and accumulate these Millicharged particles further in your lab. So this is also something we are exploring right now with experimentalists. So let me summarize this. I hope I've convinced you that there is a thermal terrestrial Millicharged population, which the Earth makes for itself as soon as you put Millicharged particles in a Lagrange. It's an irreducible population of cosmic rays, right? It's very similar to a collider in its robustness. The only difference is that production and detection are a few billion years apart. Okay? The fraction can be much smaller than 1. Nonetheless, it's interesting. Its heating limits on ion traps have been studied to realize qubits, and they improve existing limits up to 8 orders of magnitude. And future dark matter specific studies are planned right now with various different ion trapping collaborations. Let me summarize the talk. I mean, this is how I would marry the first and second part of the talk, which is Photon Dark Matter or Axion-like particles and Millicharged relics we saw in the second part of the talk. Both produce stray electric fields, right? That's the point. Right? Both produce, in this case, it's like Coulomb scattering. In this case, it's like absorption, if you want. But both are producing electric fields. And they can be looked for in charged objects, trapped single ions. These trapped single ions exist because they are using in magnetic moment measurements, like magnetic moment of the antiproton, magnetic moment of the electron, right? Atomic clocks, measurements of alpha. All of these come from trapped ions. They do all various different kinds of metrology. And more recently, they have been a promising quantum computer candidate. Right? So there's lots of money and time being put in to perfect these devices.
So for the quantum computer,
Yeah.
how many qubits can they obtain for this
So today
trapped
they can
single
do
ion?
like a few tens, I think.
Few tens.
Yeah.
So do they have a plan when we get hundreds or
That's the
thousands?
hope. That's the hope, right?
Okay.
I mean, there's a lot of hope in this field. I don't know what the timeline for something like this is, but the hope is that they would be able to do a few millions.
Few million.
Right.
Oh, okay.
That's the hope.
Oh.
There's also a question of how much noise.
Right, things like that. So you see, they already saw this heating rate, right? So they're working their asses off trying to better this heating rate, right? So that's what they're doing. So what are they doing? They're doing background reduction, as we were just talking, and they're trying to build more ions, just like you asked, right? They're trying to build what are called Coulomb crystals with many ions in them, right? What are these? These are exactly what a xenon experiment is doing, right? It's trying to reduce its background, and it's trying to go from xenon 1 tons to xenon n ton, which is what these experimentalists are doing without even dark matter in mind. So I think it's a good strategy to piggyback on this for dark matter science, right? And finally, there are dark matter specific things you can do. Otherwise, an AMO trapper will not do this, which is you build larger traps, right? There is some reason why they would do this. It will reduce the heating rate. but nonetheless funny shapes like what I showed you, like bread. These are not things experimentalists are thinking about, but these are things we are hoping we can convince them can be done, and they've been very receptive to these ideas. And of course, event rates. That's again not something they're interested in. Heating rate or event rate doesn't matter. It screws up their computer. Right? But for us, those are two different signals from dark matter. So these are worth differentiating, and then maybe we'll discover dark matter with one of these devices. Thank you.
So can the Earth have a net electric charge from its
Great question. So what happens is, of course it can't, right? Because the other charge will fly in and neutralize, right? If you believe the universe is net neutral, that's what will happen, right? But what instead happens is the standard, like you could ask the same question about forget about Millicharged particles. How could the rock be net negative charge, right? And it happens because of a really funny reason. So the clouds, they, for reasons that are not super well understood, they create large opposite potential. Like, let me draw this here. Right. So you have the rock, you have the atmosphere. So it is at some plus V, this is at some minus V. But now the clouds, which cause thunderstorms, they say are instead of minus V, they are at minus 200 V and plus 200 V, say. Right. What this does is, despite this being negatively charged, it causes lightning, which charges up the Earth. Right? It pours a bunch of electrons here, making it negatively charged. And of course, the cycle, there are charges flowing this way where there are no thunderstorms, and this is the whole cycle like that. There is charges flowing this way, but there is an equilibrium cost because of this that keeps a net positive V here and negative V here. The point I'm making is, you can ask, hey, won't the positive millicharges come and neutralize this? No, because the flow of positive millicharges is way slower than the flow of negative electrons. Right? So what's going to end up happening is you're going to say 1,000 millicharges come in. Tomorrow, instead of 1,000,000, there's going to be 1,000,001 electron to compensate for the 1,000 positive millicharges that stood here. Right? So in some sense, the fact that the Earth itself has a bunch of charged particles to play with doesn't mess with the net neutrality or net non-neutrality of the Earth.
Other questions?
Yes.
So in the experiment with the like electron pinning trap that ran for 180 hours, you said you had no background events. If you had 3 pings in there, how would you have decided this is background or this is signal?
Right. Great question. So this is again not something. Yeah, maybe I should add the slide. Great question. So reinterpretation of this question. What is your discovery path? Right. That's what you're asking. Mm-hmm. Right. So we didn't scan. Right. This is not something we could do without scanning. But let's say we scan. Right. We can plot what is called the power spectral density. What is this? This is just dp d omega. Right. As a function of omega, typical noise will look white in a narrow enough frequency window, right? But dark matter is a very specific shape. There is energy only between mass and mass plus mass times 1 plus half v squared. That is mass plus kinetic energy, right? So this is a very unique power spectral density for dark matter that you will not see for any other source that I know of. Like a source that has only 10 to the minus 6 width. That's what we are talking about, right? And this is a telltale signature of dark matter which you will not see from anything else.
Okay, so I was imagining getting one single ping from a dark matter particle, but I shouldn't be thinking of that, right? This is wave-like dark matter?
This is wave-like, but your system is quantized, right? So you're still pinging the way you're thinking about. That is still corresponds to a single quantum being absorbed. But the probability of that single quantum being absorbed depends on the amplitude of the dark matter wave.
So would I have to get enough signals
Yes.
for them to start?
Yes.
Like,
Yes.
it's not something like an LHD thing where I'm just looking for like a very few TeV signals or whatever. I would need to build up a lot of these.
Correct.
Okay, that makes sense. Thank you.
Sorry, can I just? I want to add something. I mean, if you look from afar, this would still be like a peak, right? No events, no event, no event. Say 3 events in the small frequency window, no one. So that's like an NXC search. Just that to hone in, you could do more and more fancy stuff, like go into this tiny frequency and play with it.
Okay, so if I'm getting a lot of, if I get 3 events that are all very close to each other in energy versus
Right.
3 events that are equally spread out.
Right, exactly.
That makes more sense.
Right, yeah.
Yeah, so I heard some dark matter search that use the Earth orbit around the sun, so they
Uh-huh.
are looking for periodic change with
Yes.
1-year period.
Dhamma.
I'm not sure, but like,
Right.
do you expect the same type of periodic change?
Great question. So, what you would see here is if you are fast enough to do this, like let's say you did this in January and did this in April, the spread of this will look different because the velocity will look different. Okay, that's what will happen between January and June. There will be a different, slightly different amount of dark matter flowing in. So even I think the amplitude will look different, and that will cause annual modulations. Yes.
I didn't see a mention of ions for dark matter and dark photon. Have you also thought about that?
Right. So you saw the last slide of my. Okay, it's because of this. Okay, so let's look at this parameter space. Yeah, it's because of this, right? So a lot of this parameter space is going to be taken care of by this beast called DM radio. Abracadabra, which will become DM radio, will take care of this entire parameter space. You see that goes to roughly a kilohertz or so, or 10 kilohertz. So it's only below a kilohertz that you have any hope of building a new experiment. So the ion will just not be the best way to go after that.
So you can't compete in terms of sensitivity?
But that's not an experiment built yet. But right now we can't compete with this cosmology.
Okay.
That's why there are no limits just coming from the heating rate. But that said, I again went through this really quickly, I apologize. But I had one slide where the ions could be used for, so this is ions.
Mm-hmm.
So if you go below 10 keV, 10 picoelectron volt, what is that? That's roughly a kilohertz or so, kilohertz to 10 kilohertz. That's roughly where ions can be discerned, like kilohertz jumps. You can look for axions this way. So this is something you're exploring, and obviously these are ions.
So I think, let's thank Hari, and if people want to hang around and talk some more, that's fine, but let's, we've already gone over time a little bit, let's thank him for a great